So, deriving the Taylor series. Continuing on from the last video, we've got that a function can be expressed as a power series so long as those initial conditions are met. That it exists at a point A, that the series converges. So what we do is we let x equal A. If x equals A, then what happens is x minus A minus A is 0. So in other words, all of these terms disappear. If x equals A, every term disappears apart from C0. So we can say, what's the value of this constant C0 at the beginning of the power series? It's just the value of the function at A, which is why it's so important that the function exists at A. If it doesn't exist at A, we can't find out what this value C0 is. Now what we do is we start to differentiate. Remember, if this power series exists, we can differentiate it as many times as we like. So let's differentiate it once. The first differential, f prime x. Well, C0 is going to disappear. The x minus A term is going to disappear, because the x disappears, remember, when we've got an x term. In actual fact, we should use the function of a function rule to differentiate the bracket here, but when we differentiate the bracket using the function of the function rule, look back at it if you want to remind yourself, then in fact the differential of x minus A is just 1 anyway, isn't it? So we get one lot of C1, i.e. C1. Then in the next term, the 2 comes down and goes in front, which is here. Reduce the power of this x minus A term by 1, we get 1. And so on. Bring the 3 down, put it in front of the C3, power 3 becomes power 2. So that's our first differential, and so on for the other terms. Now what we do is, again, we let x equal A. If we let x equal A, all the terms disappear apart from the first term. So, C1, remember we're after all these coefficients, we found C0, now we found C1. C1 is the value of the first differential divided by 1, and we'll see that that's going to be a handy thing to think about as we carry on, because we're looking for a pattern. Right, now we're after C2, so we differentiate again in the second differential. If you look at this disappears, so we're differentiating this now. So that term disappears. Look at this again, this disappears, and we're just left with 2C2 here. Bring the 2 down, it goes in front of there. So instead of working out what 3 times 2 is, we just leave it as 3 times 2. Lots of C3. Reduce the power by 1. So c squared becomes just, x minus A squared becomes just x minus A, which is this term, and then so on. So we bring the 3 down, and this becomes x minus A squared, and so on. So now we've got the second differential. Again, let x equal A, so that all the terms involving x minus A disappear. That disappears, and that disappears. The only term we're left with is this. So 2C2 equals the second differential. So what is C2? It's the second differential divided by 2. But we can think of that as 2 times 1. Now carrying on, find the third differential. Have a look at this solution I've got here. Check it makes sense to you. So again letting x equal A, so all terms disappear apart from the first term, 3 times 2 times C3, and we get this value here. So 3 times 2 times C3 equals the third differential, and the C3 equals 3 times CF, the third differential, over 3 times 2 times 1. Carrying on, and looking for the pattern now, let's start thinking about this pattern. Look. C3 turns out to be the value of the third differential when x equals a divided by 3 times 2 times 1. C2 turns out to be the value of the second differential when x equals a over 2 times 1, and so on. C1 is the value of the first differential over 1, and so we can think of these as factorials. So we can generalize Cn equals the nth derivative of a divided by n factorial, and we have a way of finding the value of C1, C2, C3, C4 up to Cn. We just differentiate over and over again, find the value of the nth differential at a and divide by n factorial. There's only one thing we've got to be clear on, and that's this C0. So for the pattern to work, we divide by 0 factorial, and so we define 0 factorial as being equal to 1, so that the pattern works. So now we have a way of finding all these values of Cn, and if we put them into the series, the power series, we've got a way of finding all these different values of Cn. So, for example, fx equals fa. Remember, C0 turned out to be fa, so that's C0. C1 was the value of the first differential a over 1 factorial, so that's this bit here. C2 was the value of the second differential a over 2 factorial, and so on. So we can put these coefficients now in front of the terms x minus a squared, da da da, x minus a cubed, and so on. So we end up with a general expression for the function. This power series can be written as the sum of, that's this symbol here, the sum of all the terms added together, where n equals the value of 0 to infinity. So n equals 0, we've got C0, n equals 1, we've got the first differential, so this is 1. The value of the first differential over 1 factorial times x minus a to the 1, so that's the second term. Let n equal 2, we've got the second differential over 2 factorial x minus a to the power 2, n equals 3, and so on. So this is a general way of writing these terms, all these terms. The sum of all these terms added together is what's called the Taylor series. It's a way of finding a power series to represent this function fx. If a equals 0, then that simplifies things a bit. If a equals 0, in other words a equals 0 here, that's gone and we're just left with fx. So fx turns out to be the value of the function at 0 times x to the power n over n factorial. So if the function exists at 0, we can simplify things a bit and use that series there, which is called the Maclaurin series. So we now have two expressions, one for the Taylor series, which is the most general one, but in situations where the function exists at 0, we can use this series to represent our function as a power series. Now what we need to do is look at one or two examples.